Observability and SRE Part 16. This episode has 11 questions. For each question, take a moment to think through your own answer before I share a strong approach. Question 1. Scenario. GKE killed pods. Pods in a GKE cluster keep restarting with killed after a traffic increase. How would you diagnose and fix it without just raising memory limits blindly? Here's a strong way to approach it. Check kubectl describe pod for the killed reason and kubectl top pod or historical metrics in cloud monitoring to see actual memory usage trend versus the configured limit, and check whether the increase is a genuine per request memory growth, e.g. a cache or connection pool growing unbounded versus just more concurrent requests hitting a tight limit. If it's a leak or unbounded growth, profile the app, heap dump, memory profiler, and fix the code. If it's legitimate increased concurrency, right-size requests or limits based on real page 99 usage and consider horizontal auto-scaling instead of just inflating the per pod limit, since that only delays the same failure at a higher traffic level. Nice. Let's continue. Question 2. Scenario. Docker image load in CI. ACI pipelines Docker build time doubled and the image grew from 300 MB to 1.2 GB after a dependency change. How would you find the cause and fix it? Here's a strong way to approach it. Use Docker history or dive on the image to see which layer added the size, and diff the dependency log file change to find what pulled in extra weight, a new package with heavy transitive dependencies, or a build tool that shouldn't ship in the final image. Fix it with a multi-stage build so build-only dependencies stay in the builder stage and only runtime artifacts are copied to the final stage. Pin to slim or distroless base images where possible. And add a CI check that fails the build if image size regresses beyond a threshold so this doesn't silently recur. Great. Moving on. Question 3. Scenario. GKE node pool stuck in not ready. A GKE node pool shows several nodes stuck in not ready after a cluster autoscalar scale up. How would you triage and recover? Here's a strong way to approach it. Check kubectl describe node for the not ready condition reason. Kubelet not posting status, network plugin not ready, or disk pressure, and check cloud logging for the node serial console and kubelet logs to see if it's an image pool failure, a CNI or networking issue, or a quota or resource problem preventing the node from joining the cluster properly. If it's an isolated bad node, cordon and drain it and let the autoscalar replace it. If it's systemic across new nodes, check for a recent node image or network policy change and consider rolling back the node pool version while investigating, since letting the autoscalar keep adding broken nodes just wastes quota and delays recovery. Alright, next question. Question 4. Scenario. Terraform drift after manual fix. An on-call engineer manually edited a firewall rule in the GCP console during an incident, and now Terraform plan wants to revert it. How do you reconcile safely? Here's a strong way to approach it. Do not let the next apply silently revert the incident fix. First understand whether the manual change should become the new desired state or was only a temporary mitigation. If it should be permanent, update the Terraform configuration to match the manual change and run plan again to confirm zero diff before merging. If it was temporary, plan a controlled apply to revert it outside of peak hours with the on-call engineer's sign-off. Either way, treat this as a process gap. Add a post-incident action to require any console change made during an incident to be reflected in Terraform within a defined window, so drift doesn't accumulate silently. Let's keep going. Question 5. Scenario. Ingress cert expiry. Users report TLS warnings on a production GKE service after a cert manager renewal failed silently. How would you find the root cause and prevent recurrence? Here's a strong way to approach it. Check kubectl describe certificate and kubectl describe certificate a request for the failure reason, commonly a DNS01 or HTTP01 challenge failure, an expired or misconfigured cluster issuer, or a rate limit hit on the Acme provider. Rotate or fix the immediate cert manually if needed to restore service, then add monitoring on certificate expiry, a Prometheus metric or alert on cert manager conditions, well before the actual expiry date so a failed renewal is caught days in advance instead of being discovered by users seeing browser warnings. On to the next one. Question 6. Scenario. GCP quota outage. A batch job fails at 2 a.m. because a GCP compute quota was hit in one region. What immediate and long-term steps would you take? Here's a strong way to approach it. Immediately check the quotas page for the specific exhausted quota, CPUs, IP addresses, or a specific machine family, and either request an emergency quota increase through support or reschedule or shift the batch job to a region or zone with headroom if the workload allows it. Long term, set up quota utilization alerts well before the limit, e.g. at 80%, and either pre-request higher quotas for known growth or make the batch job quota aware so it degrades gracefully. Smaller batch size. Queued retry. Instead of hard failing at 2 a.m. with no one able to react quickly. Good. Here's another one. Question 7. Scenario. Noisy neighbor on shared GKE cluster. One team's workload is starving CPU or network from other namespaces on a shared GKE cluster. How would you diagnose and fix it? Here's a strong way to approach it. Confirm the pattern with per namespace resource metrics in cloud monitoring or kubectl top pod, all namespaces, and check whether the offending workload has requests or limits set at all. Unbounded requests are the most common cause of one team crowding out others on a shared node pool. Enforce resource quotas and limit ranges per namespace so no team can request more than their fair share. Use priority classes so critical workloads preempt lower priority ones under pressure. And consider node pool separation or Kubernetes network policies plus bandwidth limits if the contention is network rather than CPU. So a fix in one namespace doesn't require guessing at other teams' expense. Nice. Let's continue. Question 8. PVC with deployments. Can a Kubernetes deployment use a persistent volume claim? And what are the trade-offs versus using one with a stateful set? Here's a strong way to approach it. Yes, a deployment can mount a PVC, but all replica pods created by that deployment share the exact same PVC, since deployment pods aren't given unique identities. So it only really works cleanly with read-write many volumes or a single replica deployment, with read-write once storage. Scaling beyond one replica causes pods to fail to schedule or contend for the same volume. A stateful set instead uses a volume claim template to provision a distinct PVC per replica, e.g., data miscal 0, data miscal 1, giving each pod its own persistent identity and storage that survives rescheduling, which is what most databases and per replica state workloads actually need. Great. Moving on. Question 9. Deployment versus stateful set for databases. If deployments can also use PVCs, why do teams still prefer stateful sets for running databases? Here's a strong way to approach it. Databases need stable network identity, stable storage per replica, and ordered, predictable startup or shutdown, none of which deployments guarantee. Stateful set pods get a fixed ordinal name and stable DNS, e.g., miscal 0 miscal headless, each with its own PVC via volume claim templates, and are created or terminated in a strict sequential order, which matters for primary or replica election, cluster bootstrapping, and safe rolling upgrades. A deployment's pods are interchangeable and can be recreated in any order with new random names, which breaks assumptions that most stateful replication protocols rely on. Alright, next question. Question 10. Stateful set scale down order. What is the pod termination order when you scale down a stateful set, and why does that ordering matter for stateful workloads? Here's a strong way to approach it. Stateful sets terminate pods in reverse ordinal order. The highest numbered pod goes first, e.g., scaling from 3 to 2 removes pod 2, and by default each pod's termination completes before the next one starts. This ordered, one at a time teardown protects workloads like Kafka, Elasticsearch, or Cassandra where removing multiple nodes simultaneously could break quorum, cause data loss, or leave the cluster in a split-brain state. It lets the workload's own rebalancing or replication catch up between removals. Let's keep going. Question 11. Container root access. How would you prevent processes inside a container from running as root? Here's a strong way to approach it. Set a non-root user at the image level with a user directive in the Docker file, and enforce it at the cluster level with a pod security context or container security context setting run as non-root, true and a specific run as user or run as group, plus allow privilege escalation, false and a read-only root file system where possible. To make this a hard guarantee rather than a convention, enforce it with an admission controller, pod security admission restricted profile, gatekeeper, or Kyverno policy. So pods that don't set run as non-root are rejected at admission time instead of relying on every team remembering to set it. On to the next one. That wraps up this episode. Nice work practicing, and see you in the next one.